We've got Hussien AbdelRaouf Khaled. He's another one of our research competition winners. He'll be talking about empowering AI-driven healthcare with secure, decentralized, and privacy-enhancing adaptive intelligence. A round of applause.
Thank you so much. Hello and welcome everyone. My name is Hussien AbdelRaouf, PhD candidate at Augusta University, Georgia. And today I'm genuinely excited to present my presentation titled Empowering AI-driven healthcare with secure, decentralized, and privacy-enhancing adaptive intelligence. So here is an overview of what I'll be covering today. Starting with introduction, giving a brief intro about healthcare system and how it works, and then followed by research background, existing limitation, and then the proposed methodologies to overcome these limitations, and then lastly we conclude up our work. So as we know that the integration of recent cutting-edge technologies, including Internet of Things, artificial intelligence, cloud computing, has revolutionized the way healthcare system works. And this integration has led to what we now call Internet of Medical Things, which is specialized in enhancing healthcare system through delivering health monitoring and disease diagnosis. And this shows a figure to provide a graphical representation of health monitoring utilizing wearable sensors. So as you can see here, that the wearable sensors are implanted into patient body, which are responsible for sensing health signals like heart signals or activity signals. And then these, and these signals are fed into two different deep learning models for detecting heart attack or recognizing activities. So here we just provide a research background about maybe a laptop. So there are many different types of deep learning, like CNN, which is specialized in extracting spatial features, or in LSTM, GRU, which are specialized in extracting long-term dependencies. And lastly, transformers attention mechanism, which assigns high attention to key features. So first, we will address the problem of adaptability. So what does this mean? This means that the traditional AI models are static and cannot adapt to evolving health data. And because, data distribution changes over the time, especially data streaming. So this phenomena is called concept drift, which means shift in data patterns over time. And this degrades the model performance, accuracy, and so on, which negatively impacts health monitoring. So to address this problem, we provide this figure, which provides a comparison between the traditional AI models, offline learning, like training dataset followed by training deep learning model and then prediction, and our proposed online learning that we just monitor the drift or monitor the deep learning model through either data distribution or model confidence. So we provided or proposed this module, which is called ALDD, Adaptive and Lightweight Drift Detection Module. So we have two phases, the offline learning phase and online learning phase. So during the offline learning phase, we train a deep learning model, HAR model, which we will discuss this later. And then we were trying to learn the model confidence threshold. So we've utilized this equation to compute this model confidence threshold, which is the average of models' predicted probability of correctly classified samples, in which y actual equal y predicted, given x double. So to put it simply, this measures the confidence of the correctly classified samples. So now, after learning model confidence threshold, we have the online learning phase, in which we have a data streaming and then model prediction, then getting the model confidence, as we can see here. There's the person. So after that, we compute the counts of the all samples in which their confidence exceeds the confidence threshold. So now, after computing the counts of all samples that their confidence exceeds the confidence threshold, then we have to check if this count of samples falls below a specific drift threshold. And in this case, then we detect a drift. Once a drift is detected, then we trigger a retraining process. So this is the proposed deep learning model, HAR model. So as we can see here, we have utilized three modules: spatial module, attention module, and classification module. So spatial module, we've utilized convolutional neural networks to extract spatial features, and the attention module, in which we utilize GRU block to extract long-range dependencies, followed by multi-head attention to assign high attention to key features. And then we concatenated these results or these extract features together, and then followed by classification block or classification module to classify these or to predict the activities. So here we just conducted a population study, and it's obvious that CNN and GRU separately achieve modest performance, while combining CNN and GRU further improved the performance. And lastly, integrating multi-head attention to the CNN and GRU achieves the best. And then the table on the right just further verifies the results. And here just a comparison between the proposed model with the previous state-of-the-art techniques. And it's obvious that the proposed model achieves the best in F1 score and ACC accuracy in comparison with the previous state-of-the-art models. Importantly, it does this with only 57,000 of parameters, highlighting efficiency. And the table on the right just verifies these results on another different dataset. So, sorry. I think that's because Mac.
Yeah, it's sometimes.
Yeah.
It's unfortunate.
Okay, so we have different limitations. The first, privacy preserving approaches, in which most of these approaches suffer from high overhead, especially communication overhead and computation overhead, which is a big problem especially for resource constrained IoT devices. And second is security risk, in which attackers could exploit this phenomena of concept drift to inject malicious or false drift to trigger unnecessary retraining and then waste computational power. Also, weak anonymity and unlinkability, in which most of the previous blockchain technologies or blockchain techniques or networks lack data unlinkability and patient anonymity, in which attackers could correlate or correlate multiple patients' data together to unfair sensitive data. And lastly, secure retraining. So once we trigger retraining, the attackers could exploit or could infer some sensitive information during the retraining process, during epochs, forward and backward, especially during updating the weights or gradients. So we will start. So here we just present the network model. As you can see here, the patients who are responsible for encrypting and sending health data. The medical centers are responsible for health monitoring, for concept drift detection, for secure retraining, and we have also blockchain, which is responsible for preventing false drift claims and unnecessary retraining, and also responsible for validating block generation in the network. So here we have threat model, external adversaries like eavesdroppers, or internal adversaries, which are honest but curious medical centers or malicious compromised medical centers. And lastly, model retraining vulnerability. So which the attackers could exploit this vulnerability during retraining to exploit sensitive data. So our goal is to preserve a preservation during the health monitoring drift detection, also to prevent false claims and avoid unnecessary retraining, and lastly to ensure patient anonymity and data unlinkability. So this is an overview of the proposed methodology to overcome the previous security and privacy problems. We will go through each step or each module and discuss it in details. So for now, we have module number 1, which is just for initialization between patients and medical centers. Module number 2, responsible for generating encrypted data. And then module number 3, running HAR model, which we've previously created and designed, and BMTT for privacy preserving health monitoring. And then module number 4 to run ALDD, adaptive and lightweight drift detection, which actually we mentioned before and discussed. And then module number 6 to verify this drift through blockchain or TCDD, trustworthy and collaborative drift detection module. And once the drift is approved, then we run module number 6, BASR, for preserving the privacy during the retraining process. So now we will go through each module and discuss it into detail. So actually we presented this before. This is the first limitation, privacy preserving approaches. So we have many different techniques like homomorphic encryption, secure multi-party computations, or differential privacy, which adds some noise to the data to avoid being attacked or or the attackers could infer some sensitive data. So first, the initialization phase. So which is we're trying to exchange the cryptographic keys between the patients and the medical centers. So first, the patients generates a secret key for each time slot, and then second, the medical center sends the weights of the first layer of the proposed deep learning model to the patients, and then the patients utilize these weights to generate decryption key utilizing this equation. So G1 generator to the power S secret key times weights, and after generating this, the patient send this decryption key to the medical center. So now patients start sending their encrypted health data utilizing this equation for encryption. G1 to the power UL, which is the hash of time slot, times S secret key plus T, text data. So now the medical centers, after receiving the encrypted health data, the medical centers evaluate the proposed deep learning models through utilizing inner product functional encryption technique. And this is just a mathematical proof for this evaluation. And lastly, here we obtain G1 generated to the power summation of D times W, plain text data times weights. And then we utilize discrete logarithms to obtain the power, D times D, summation D times W, times W, plain text times weights. So this is the, I think the laptop has a lot of mistakes. Yeah. So after obtaining these results, which are the output of the first layer, and then these results are fed into the next or subsequent layers for predicting the output. As you can see here, this is the encrypted encrypted data, and then will be multiplied with weights without revealing privacy, and then we obtain the values of the first layer, and then in which these the results will be fed into the next subsequent layers. So now, module number 4, actually we've discussed this previously, adaptive and lightweight drift detection module for detecting drift. So now once drift is detected, then we have to verify this drift using blockchain, trustworthy and collaborative drift detection technique. Yeah, actually, so now we're targeting or addressing the security risk and anonymity in patient data unlinkability. So we'll start with this module, verifying this drift through utilizing blockchain through TCDD, trustworthy and collaborative drift detection module. So we have 4 modules: initialization phase, in which the patients are grouped together and assigned, each group is assigned for a specific medical center, and then the medical center start generating public and private keys, and then 3 medical centers are randomly selected as cycle leaders. 2 of them are used to generate cryptographic keys for generating group signature, and the 3rd one is responsible for overseeing the decision-making process. So phase number 2, which is group join phase. So the patient picks a secret number and send it with his ID to the medical center, and then the medical center starts generating patient private key utilizing random secret XI and ID. So now data sharing phase, in which each patient stores sending a signed and encrypted message, as you can see here, sees ciphertext, and OR, which is a unique random value responsible for preventing data linkability, and T times dot, and sigma, which is group signature to preserve data integrity and ensure authenticity. So the last phase with us is drift detection message. So if drift is detected, then the medical centers share this message, P or T sigma. B is the drift causing patches or unique random number, T times dot, and sigma, which is digital signature. And once the drift is detected through voting between all medical centers utilizing a PBFT, practical Byzantine fault tolerance, to authorize retraining. So once 2/3 of honest medical centers approve this then the medical centers generate retraining the model to update it. So lastly, the leader broadcasted this updated model to the whole medical centers for inclusion in the model update ledger. So the last limitation with us is secure retraining. So we just try to secure retraining process from attackers exploiting this epochs to infer sensitive data from weights or gradient updates. And this is the last module with us, running PASAR, privacy preserving and adaptive secure retraining process or retraining module. So here we just customize or tweak the previous cryptographic technique to be more robust against attack, especially during epoch retraining. So first, each patient generates a new drift key utilizing a new time slot and the weights, new weights for each epoch. And second, also each patient encrypts the ciphertext data utilizing a new time slot and the new data, the drift data. And lastly, the medical centers evaluate this utilizing the inner dot product as we explained previously, using the new time slot in new weights. So here we present the results and evaluation. So this figure just provides a comparison between the proposed model confidence and benchmark Wasserstein distance, which measures the distance of the data distribution between two consecutive batches. And it's obvious that, for example, at batch 20, when we injected normal drift, then we could notice that there is model confidence drop. And whenever this drop is detected, then we trigger retraining process to recover this confidence, as we can see here. Notably, Wasserstein distance achieves around a total time of 3 seconds for 225 batches, while the proposed ALDD achieves around 1.4 seconds for the same number of batches, achieving around 52% reduction in computation time. So here we evaluate the computation and communication overhead of privacy and privacy preserving drift detection approach. So computation overhead means that the time taken for encrypting and decrypting the cryptographic keys at both the source and destination. And it's obvious that the proposed scheme takes only 34 milliseconds, while the PHE takes around 6 seconds. And this has been provided at the patient side on Raspberry Pi for Model B. And also we've calculated the time required at the medical centers. And it's obvious that the proposed model takes around 0.3 seconds, while PHE takes around 5.4 seconds. And on the other hand, communication overhead, which is the size of data taken for encrypting and decrypting the patients. So for encrypting the data, our scheme takes around 56 bytes, while PHE achieves around 512 bytes. For dataset with 25 features, the proposed scheme takes only around 1,400 bytes, while PHE study takes around 12,800 bytes, highlighting the efficiency of this proposed scheme. So here we present the results of the blockchain. So as we can see here in this figure, that the data block size increases proportionally with the number of batches in a like linear relationship. And even though this overhead could be managed due to the computational power available at the medical centers. And lastly, we conclude So actually, we provided an efficient deep learning model for improving health monitoring, and then adaptive and lightweight drift detection module, and then a privacy preserving and lightweight module for preserving the privacy during health monitoring and drift detection, and lastly, a customized blockchain to prevent malicious data drift and to ensure patient anonymity and data unlinkability. So this work has been published in prestigious journal IEEE Internet of Things, which is Q1 high impact factor, and also has been published at flagship IEEE conference, ICC. So that's it. Thank you for your attention. Look forward to your question. Yeah. About the malicious or yeah, that's this for like specific like for example COVID-19. Do you remember that there is a the distribution of the data has changed, you know, especially IoT sensors, a lot of people starting to die and so on. So maybe there is a different distribution of the data. So this could be detected by the adaptive models in which there is a change in the data distribution, and in this case the model performance will degrade, and in this way we could detect the drift. Yeah, on the normal cases, maybe due to IoT sensors, or maybe due to the conditions of the environment and so on. So this could happen in any environment, you know. You mean localized or could be generalized in different environments? Yeah, for our case, we've utilized or we've used these datasets in a specific case for healthcare systems, but you could apply this for any different systems. Once you have datasets and you have your data, then you could apply or run these models, but you need to monitor these models specifically on your data. This distribution is totally different than this. Yeah. Actually, we've considered this concern because when we trigger retraining, we not only retrain the model of the drafted data only, but we consider also the historical data sets, so that we could not forget the historical data. So the retraining process, we take the historical data with the new drafted data, both of them together. So the model is still able to identify the new data, new distributed data, and the historical data set as well. Does it make sense? Yeah, as
Yeah, no,
I mean,
it's
I understand
all-
that
I understand.
that there is. You mean that there is different distribution, right?
Well, so
Very dirty.
not necessarily.
No,
dirty,
you
but-
mentioned. But I think, for example, human activities, for example, it's the same. It's the same in everywhere else on the planet, right? So this maybe fit with application like this, or maybe heart attack signals. So it will be the same everywhere else. Yes, this depends on the data set and which specific people you're targeting. Maybe you have a specific model for this kids, or maybe another model for older people. Maybe yes, exactly. Training data set like
Yeah,
pre-processing. Oh, the blockchain. Yeah, yeah. You know that blockchain structure is like a tree, transaction, and has a hash code, and then another tree with another branch with transaction, and then hash code, and so on. So we could prune these transactions. Yeah, just prune it. You could just reserve the hash code of this transaction, but you could remove it. Yes, exactly. Yeah, this is popular techniques for pruning these transactions without compromising the blockchain security. Yeah. It's natural. It depends on normal. There is normal distribution. We need to verify that if this model is able to adapt to new drift or not. So you need to inject some drift, normal drift. Yes, injecting. Yeah, exactly. 5 times we injected different normal distribution to check if this model will be able to detect this drift and adapt to it. Actually, yeah, you have the previous model stored in the blockchain. Yeah, to ensure the transparency. Just only the data causing drift. This is just loaded on the blockchain. For the whole other medical centers to verify this with the model causing the drift. To ensure transparency between all the medical centers. Thank you. Thank you.